let's see, is that smaller than it usually is? So, and I know that's what I thought it was. It's like, I don't know if it's because those stupid pictures are up there. I don't know. You can see it, I guess, but okay. So we're going to study something now that's really interesting, and it's something called statically indeterminate loading. Make sure you take a close look at that syllabus. Ian, I just gave you kind of an updated syllabus that's in front of you there. You missed a little discussion about that. So I want you to have a sense of what statically indeterminate is, and it's very closely related to what we just studied, but it's very interesting. And so would you agree in this picture? So I got this bar that's 5 meters long apparently, and then somebody comes along and puts a 500 Newton force, in a certain location on it, kind of starts pulling down. And of course, because that happens, what we looked at last time is that's going to make the shape get longer or shorter. Well, and the weird thing is does it make sense that this section up here kind of wants to get shorter? No, I'm sorry, I said that wrong, didn't I? It's being pulled away from, so therefore that's in tension. This wants to get longer. Does that make sense? But then this section, it's kind of being smashed, so this wants to get shorter. But the interesting thing is because it's pinned on both sides, it's actually not going to get shorter. Isn't that weird? So if it was freestanding or not touching something, then it would get longer and shorter. And that's kind of what we said before. We sort of had these free body diagrams where we just had some piece of metal here and we said, hey, let's pull on it. It's going to get longer because you pulled on it. But if you pull on it and you say it's stuck to a wall, then it's like, well, now what's going to happen? Well, it's not going to get longer. It's going to try to get longer, but it just won't be able to, right? And that's because there's basically forces attached to this that are kind of pushing back. I mean, this is attached to something. So does it make sense there would have to be down here kind of a force at B that's pushing up on that because of the 500? Now the force at B would be nothing if there was no force on the pipe. It would just be sitting there. Well, maybe it has some weight if it's vertical and that causes it. So that's going to have to push back. And then we're not really sure what direction A's force would go, but I guess maybe we are, because isn't this trying to pull down? So wouldn't this have to pull back in that direction too? So maybe we are sure. Do you agree with that logically? So then if I said, okay, well, great. Then since this thing is actually static, then what are the sum of the forces in Y? Well, I have force of A going up. I have force of B going up, and I have 500 going down. So I have that equation. Do I like that equation algebraically? I do not like that equation algebraically, because there's a lot of different answers for force of A and force of B, but doesn't it seem like there should be some way to calculate like how much force is at each one of the, I mean, I got to glue this to the wall, right? You don't just get to say, hey, it's stuck to the wall. Like as an engineer, you got to stick it there. You got to put some bolts on it. You got to glue it. You got to weld it. And if you don't know how much force is actually at A and B, then it might rip off the wall, right? You didn't put enough bolts there. So it feels like I should be able to do that somehow, but it's like, clearly this isn't going to work. I don't really have any way of doing it. That's what being indeterminate means. Statically, isn't that a static equation I said right there? The sum of the forces in Y have to be 0. That's what static says. Hey, let's not have this thing moving. But then it's actually indeterminate. I can't determine how much of the 500 is each one's carrying. Is it 100, 400, 300, 200, 1, 499? Or do I have one backwards? It's 600, negative 100? Because I could have it backwards. But it's like, that's not good. This is not determinate. Do you find yourself, laughing a little bit when you look at the chapter title sometimes, like humans, like what? That's what the section's called, statically indeterminate axial loading. But does that start to speak to you? Like, what's axial mean? It means lined up with the axis of it. And yeah, that 500 is in line. Notice it's not coming in sideways, which would be shear, right? It's an axial, and then it's loading 500. So actually, as weird as that statement is, and I want you to understand that. I find myself, when I'm teaching myself this, reading those sections and going, what? And then I get into it, it's kind of like, oh, I guess that name makes sense. I mean, it's weird that you'd come up with such a crazy name, but.
Have you ever run into a real life statically indeterminate load?
Yeah, this is actually all the time because stuff is pinned like this all the time. Like, isn't a bridge pinned at both sides? And then you start pushing and pulling on it.
How do you spec out the substance that it's pinned against?
What do you mean? Because it might pull on it. Like if it was attached to rubber, then what it was attached to would stretch. Is that what you're saying?
Well, I just think, like, let's say this is exactly how the picture depicts it, but let's say the substance of A and B that's pinning it is wood. And
Right.
it doesn't have the PSI to withstand.
Yeah, then it's going to stretch. It's going to statically, it's going to deform, just like everything else we're studying.
But if it's indeterminate, how do we choose whether it needs to be steel or concrete or wood? Like, how do we know?
Well, in the end, there is a way to determine how much force of the 500 each of them takes, and that's where we're going with this. And then we'll be able to say, okay, well, then let's make it out of wood or steel or
I
whatever.
thought we were just like, oh, it's indeterminate. We're going to leave it that way.
Yeah. Well, that would be really problematic because you're exactly right. If we can't determine how much of that 500 is in each location, then we can't choose the right weld, like it'll break. And actually what we just studied is the answer to that question. So let's take a look at it. Notice I said the reactions at each support cannot be determined, ... or can they? Isn't that exciting? Woo! So statically indeterminate, meaning we can't determine how much of the 500 newtons each end takes if the bar is to remain static. But let's take a look at this a little bit more. So notice I stole this right out of the book in terms of the pictures, but it's just, you know, I'm going to make my own calculations about it. And so here's kind of the trick to this, if you will. And it's not really a trick. Let's see, where am I? Now, here's what we did before. And this is what I want you to think about. Before, in the previous section in 4.2, let's just remind ourselves, we basically said, okay, I sort of have like 3 places that are interesting here. There's stuff happening right there, right? So that's kind of cool. And awesome. And so we then come back and say, okay, well, let's sort of figure out what's happening in here, right? We kind of chunk it somewhere in there. And if I was to kind of draw that, would you agree that that little chunk, force of A right there, to where that cut is, does it make sense if that is to remain static? The 500 hasn't got there yet. This is a really important idea. This is the concept of sections, the fact that, and that's really the whole thing this class is about, is saying, hey, you know, in order to pull with this in 500, I got to kind of look inside this shape and kind of see what it's going to do. Is it capable? Does it have the PSI strength to withstand that? And the answer is no, it's going to get a little longer or shorter, maybe microscopically. But when I chop this right there, for that to stay static, does it make sense automatically? Those have to be static. Therefore, that's all I got so far. The 500 hasn't got into the picture. And so if I call this A and this B and this C, no, I guess I better stick with what they set up on top because they already labeled it. They call that C. So really what we're talking about here is from A to C, or just short of C. If you make it to C, then the 500 is in the picture, right? So that's a section any place in there. And so then didn't we, isn't this what we said the other day? We said, hey, the delta is equal to, is it NL over AE? Was that it? I think that's it. We said, and I would encourage you to go back and reconsider that equation is actually not brand new. I showed you that a little bit the other day, but whatever, we have 500 equations to stare at now. There's another one of them. Delta, the change can be, and notice it's kind of cool algebraically to think, what is the change a function of? Well, how much force, how many newtons, and how long is it? And what's the cross-sectional area? And then what's the modulus of elasticity? How elastic is the material? All of those things are going to play into whether it wants to get longer or shorter. Notice in this case, because this is under tension, that my sigma from A to C, I'm sorry, not sigma delta, from A to C is actually going to be positive, isn't it? It's going to get longer. It's not going to get shorter. And so what are my forces? Well, my force is force of A. My length, I'm told up there, is 2 meters. And my area, let's see. That's interesting. Notice there's no information about its area. So I'm going to write A for area. And then we're also not told, like, what is the material? So I don't know. I guess I don't know for now. I can make something up, but I did this on purpose. So I'll show you in just a second. But would you agree that's how much longer it's going to get? The problem is that doesn't help because I don't know what force A is, right? This doesn't really help. This doesn't do anything. That's great. You wrote that down, but good job. No help whatsoever. Well, now let's jump down here to this second cut. Where we're going from C to B. And I have two choices for what to call this force. Would you agree that I can say, well, it had force of A going in this direction. And now because we made it past 500, then we also have 500 going in this direction. So we have two forces to add together. And that would be, if they're both numbers, it would have been made a lot more sense. But does it make sense instead of that, if I wanted to, I could just kind of say, well, let's just look at the other end. In other words, if I look at B, doesn't it have, instead of looking at it as the top part of that, I'll just look at it as the bottom. Would you agree this is force of B down there? And therefore, isn't it also up here? Because that thing has to remain static. So notice the 500 isn't even in it. And so, well, then don't I have the same exact thing? But notice this is under compression this time. Therefore, it's actually going to get smaller, isn't it? So delta from B to C is actually negative. So that'd be force of B, its distance is 2 meters. But again, I don't know anything about A and E. So the question is, does that help? Because part of me says it doesn't help. Like all I did was just write another equation that's got force of A and force of B in it. But what's true about those two distances that we just calculated, or at least we wish we could calculate? What's true about those two? They got to be the same because nothing actually moved. Does that make sense? It's not getting any longer because it's hooked to the wall. Yesterday, the plate was out in midair and we just pulled on it. And so it really did get longer. This thing isn't getting longer. So because it is pinned, I'll just leave it at that, pinned at both ends. It's pinned, so actually delta AC is actually going to be equal to delta BC. They're going to be the same. However much longer one of them got, the other is going to get that much shorter. Does that make sense? Now I could just add them and set them equal to 0. I've got a positive one and a negative one, and add them and set them equal to 0. Or I could just say what I just said, sort of like forget the negative sign. One just got bigger, one got smaller. Those two, whatever those two numbers are, numerically getting smaller, larger, they got to be the same. Well, that's my second equation. Like I have two equations, two unknowns now, and so I actually can determine it, which is rather cool. So it's the fact that we know something about how things get longer. We stare at this problem and we realize, hey, it's not just that those two forces have to add up to 500. It's also that when you add a force to something, it's going to deform. It's going to get longer or shorter. And because in this case, we can say, no, it isn't. We can say it isn't going to get longer or shorter. Then that allows us to come up with a different answer. And so your book calls this, so I think I'll just, in the interest of time, notice I'm leaving the negative sign off by the way that I'm choosing to do this. And I'll go ahead and write this in here too. Either of those two would do the same job. Does that make sense? And there's part of me that thinks that other one, the one I just wrote, is probably better because I already took the time to say one is positive, one is negative, and they have to add to nothing because it doesn't move. Taking the negative sign away and setting them equal is, part of me likes that better. but they're both true. I mean, algebraically, couldn't I add delta BC to both sides and I'd have the same equation anyway? You see what I mean?
Would we have a 3 for the second BC instead of 2?
Yes, we would. Thank you for catching that. This was not 2, it was 3. Now, interestingly, so we actually have 2 equations, 2 unknowns, but what do you notice if you're just solving these algebraically? Think of that as an algebra problem now.
The area and the rest of this thing.
Yeah, notice they don't matter. Like if they had told me, I would have wrote them in there and had all these huge numbers, but it wouldn't have done me any good anyway because I didn't know what force of A and force of B are. But it's like those end up just canceling out. It's kind of like, who cares what the area is? It would have mattered had the area been different though. Does that make sense? Notice their areas are identical because it's the same bar all the way through. It would have mattered if they had a different area and if they were different material, but they aren't. They're the same material. So that would have canceled out anyway. So I really have 2 equations, 2 unknowns then, and that can actually answer this. So. And this is meant to be an introductory problem, so things come out nice and clean here. And is it a coincidence that it was like 2 and 3 for the distances? Like proportionally, one was 2/5 and one was 3/5, and this is also 2/5 and 3/5? The answer is no. However, a lot of times you will have different materials and different sizes and so forth, and then you can't just it's not quite as easy as a proportion. But notice that's kind of proportionate here. So your book will call this, I don't know if I'm going to use this terminology, but a compatibility equation. And I suppose they're using that language because those two sections are compatible. They have to like get along, live in the same house, so to speak. They're in this together, so to speak. And so, who cares what it's called? But isn't that kind of cool that you actually, it looked like there's no way out of this mess. I know they have A and B have to add up to 500 collectively, but there's no way I'm ever going to be able to figure out what they are. But it should make sense to you that when you put a force on something, it's going to change size. So isn't there something else we can look at here? That's kind of cool. The printer for school was dead, so I don't have a copy of this for you blank. Let me see which one I want to do first. Let's do this one first because it's more like the one we just did. So just to stare at this a second, would you agree that's the same thing we just looked at? It's identical. And remember, that little plate unit is only just in there to put 16 kilonewtons on it. It's really the same exact problem, it just has 16 kilonewtons sitting in there. Notice at a glance, it looks like the material is the same size all the way through, just like the example I just did. It also looks like it's the same material, like they didn't change the color. I wonder if that's the case. They said the A36 steel pipe has an outer radius of 20, inner radius of 15. Oh, that's interesting. So it's hollow. And it fits snugly between the fixed walls before it's loaded. Determine the reaction at the walls when it's subjected to the load shown. That's the same. They're saying it's the same. It's A36, so it's a material this time. Before it wasn't. And then they're telling us it's hollow and they tell us the dimensions, but it's the same problem. It's not any different. So let's just see if we can figure this out. So again, based on the logic of this, I'm saying, well, to me, that looks like, I'm gonna write it normal at A instead of force at A this time, just because it is perpendicular. We do call that normal, right? So whatever, it doesn't matter. And so on the left, I clearly have that pointing the right direction because it's trying to counter that 16. But then over there, the B is pulling away from C. So isn't this going to have to pull back? If you get that wrong in your free body diagram, you'll just get a negative number. Then it'll tell you you did it wrong. Now you get the right answer still. But in this case, logically, I can tell that's true. So I know I'm going to get positive answers for this. But remember, negative answers don't mean anything. They just mean, oh, arrow's wrong. Leave the diagram alone, just leave it negative. Okay, cool. Well, if that's the case, then my initial equation is, and I'll just write it, I'm going to do this a little faster, but it's like n of A and n of C are pushing to the right. And wouldn't they have to equal what's pushing to the left? So I didn't write this as the sum of the forces equals 0. I just said, hey, 2 of them are pushing to the right, 1 of them's pushing to the left. They got to balance in order for that thing not to move. So there's my first equation. Where does the second equation come from? Well, I chop it right in here. And I say, okay, cool. That means that delta from A to B is the normal at A. And I think I will take the time to just redraw that section just so that you realize kind of how important it is to at least have in your mind a free body diagram. Remember, that's a cut, that is a chop in the middle of the steel, which means that chunk of steel right there is going to have to be capable of pushing back or this thing's going to fold. So I have that force times its length, but 300 millimeters, maybe I should be changing it to meters, I don't know. I have an area this time. But notice, because just like last time, it's the same all the way through. So rather than put that in there, I'm just going to do what I did before out of laziness. So the fact that they told me what material it is and what size it is, I don't even care. I don't even have to calculate that. And then I chop it over there. And so what does that equation look like? Well, now it's whole on this side, at least I think, with n of C pulling this direction. I come over here and it's got kind of a chop out of it. And so then it must be pulling n of C in that direction. So what's my delta from B to C? It's my normal force at C, but that's much longer, 700 millimeters divided by the same AE. Okay, cool. There's my compatibility equation. I could set those two equal to each other. Oops, something's wrong. And just like last time, those cancel out. So it's a good thing I didn't waste my time. So, 2 equations, 2 unknowns, boom. Doesn't come out so nice this time. You get normal of A is 11.2 kilonewtons. It's a decimal. Normal at C, you get 4.8 kilonewtons. Now, what I'd like you to stare at for just a second, though, is notice one is like way bigger. Does that seem correct? Like, why would one be so much bigger? I mean, my gut reaction is, wouldn't it just be equal? Shouldn't they both be like half, 8 each? How come NC got so much more? How come it had to work so much harder? That's exactly right. It has entirely to do with these 2 numbers right here. One of them is twice as long. Remember, its deformation is a percentage. So if that percentage was, say, 10%, isn't 10% of 700 a lot more than 10% of 300? It's trying to get longer. Because remember, this section right here is in tension. And this is in compression. So one got shorter, one got longer. But it's more than twice as long. So the fact that it had to work twice as hard as a result of it getting longer. Incidentally, does it make sense B actually would move here? You could actually calculate, where does B end up? It starts out at 300, and then you put this 16 kilonewton force in it. It's not going to stay there. A and C are going to stay hooked to the wall, but that little collar or whatever it is actually not going to stay in the same location. And now that you know what NC is, does it make sense you could actually calculate that? because they did tell us what kind of material it was. We know NC now is 4.8. Actually, that's backwards from what I just said a second ago. Actually, I just assumed. I thought, hey, this is way longer, then this is going to have to be bigger, but that's actually backwards. It contradicts what I just said. Do you agree with that?
Just kind of having trouble with it too.
I mean, I'm just trying to make sense of it out loud. So now all of a sudden I'm thinking what I just thought I thought made sense. And now all of a sudden it's like, no, it's actually backwards. NA had to work way harder, but it's way shorter. Huh, now I'm lost.
So when you say like algebraically, I'm struggling. You have two equations, two unknowns. Are you putting NC times 700 on the left and equaling it to 0, and then kind of have like NA plus NC equals 16, and then NA times 300 plus NC times 700 equals 0?
Yeah, I mean, in the end, you could take, to make them kind of look the same, you could say 300 NA minus 700 NC equals 0, and then you could use a matrix, because
Yeah.
maybe I wrote them backwards. I could have. I mean, I calculated this at my desk a couple of days ago or whatever. Maybe I wrote them down wrong. Maybe they're actually backwards.
The correct answer, though.
It is, right?
Yeah, I was struggling. I wanted to put it in a matrix, you know, and so I was like trying to figure it out. And I
Yeah.
forgot the minus becomes important if you do it that way.
Yep, that's absolutely true, because matrix only works if you get them all lined up. N of A is first, N of C is second, equal sign, number on the other side, it's got to be just the same.
So is NA not working harder because the force is closer to it? I guess it shouldn't matter, right?
I mean, NA is working harder. That's the answer we think we're getting. Like, we got 11.2 for this one, and we got 4.8 for that one, if I didn't screw it up. So now my gut reaction is, again, I'm always just trying to make sense of stuff, because that's what makes this stuff stick with you longer. So, and like I've told you, this is brand new for me too, so that feels counterintuitive.
I guess because there's less between A and B, that force is being just like moved through it at like a greater capacity, sort of.
Yeah, it's kind of like there's less bar to do the work. Like,
Yeah.
it's got 16 pushing on it, and there's not very many people there to resist it. Maybe that's the answer. It's a good thought. I mean, it does make me want to calculate all of that. We actually probably have time. Let's do that really fast. I won't type it in, but now that I know this answer, I'm actually gonna go back and figure out, maybe do this with me just to see, make sure I don't screw it up. What does that mean delta AB actually is, if I just type in everything?
Algebraically, it makes sense since you have a smaller number on top, you're going to get, actually. Never mind, keep going. Okay.
So let's see, A would be, and when I look up E in the back of the book for, what is this, A36 steel, and this is metric. A36 steel, this is metric. 70, it's 200, is that right? So it's gigapascals, which remember means a million, if I remember right, 10 to the 9th, no, billion. Million, billion. 9 zeros. I'm a math teacher, I don't know if I've ever seen a billion and a million. And a Pascal is Newton per meter squared, right? And so I need the area to be meters squared for that to cancel out. So 200 gigapascals. Some respects, I'm not, I wouldn't say stalling, but I'm just like, I want to understand this. I want to think about it. I want this to make sense to me. There's no reason it shouldn't. I should expect things to make sense. So that's true. And then the area then would be pi times radius squared of the outer, because the outer radius was 20 and the inner was 15. Thank you for giving me radiuses. That's 0.02 squared minus 0.015 squared. So that'd be square meters then, right? Whatever that is. So now I can type all that in. Sigma AB, delta AB is NA, which we said is 11.2. Notice that's kilonewtons. Is that a problem? Yes, because isn't E in newtons? So I'm going to change 11.2 to 11,200 when I type it in. So 11,200, and I can leave those millimeters alone because it means the answer will come out in millimeters, which makes sense because it's not going to move much. So notice I'm going to end up with just millimeters for an answer to this. So times 300, then divided by, and I'm going to say divided by pi, and then divided by 0.02 squared minus 0.015 squared, close the parenthesis, and then divided by 200, and then divided by 10 raised to the 9th. If I didn't type any of that in wrong, I got 0.03, 0.0306.
Was the diameter given?
Yeah, it was hollow. Outer radius of 20, inner radius of 15. I want you to think about what I'm writing here. BC equals, okay, same exact thing. So I should be able to go back and just retype what I just typed. What am I going to change though?
Change the 11.2 to
That's exactly right. So instead of 11.2, I'm going to type 4,800
when you also have to change the distance.
in the distance as well. 40, that's exactly right. That and the distance. When I did that, I got this. Oh, of course I did. They had to be equal, right? Remember, one of those is actually positive and one is negative, though, technically. Technically, this one right here is actually negative, right? Because it's under compression. So basically, BC got larger and AB got smaller by the exact same amount. So therefore, the pipe didn't change length, which it couldn't because it was stuck to the wall, right? But did the collar move? Yeah, BC got longer. It moved 0.03 to the left then. You agree with that? So that line right there went 0.0306 to the left. So it did actually, that moved. I mean, the pipe, you wouldn't see it, but the pipe is changing size. Isn't that weird? It's just the sides are still attached. So it's like, oh yeah, of course I got the same answer for both of those, which by the way, only occurred to me like right as I was about to make the calculation. I was like, oh, these are going to come out the same, aren't they?
So it's just a ratio between the amount of force and distance that's going to be giving us the two different.
Yeah, in this case, because the material stayed the same, but they won't always stay the same. So you kind of have to go through these motions. Let me just show you one other thing out of interest. You actually don't have to do this problem with two equations, two unknowns, if you don't want to. I hesitate to show this to you, but do you agree that one equation, one unknown? Like, what if you never did this equation on the top right here? What if you just did what we did down here? The question is, did I have to label this the way that I did? What if I thought of this section right here a little differently? So I'm going to copy this down below. What if instead of doing that, I said, well, let's just keep working from the left. Would you agree that I kind of worked that one from the right, just so that I made that equation a little easier? But what if I kept doing this from the left? And I still had that N of A over there pushing on it. But I got to a certain place and there were 16 kilonewtons right there. Does it make sense? I got past that now. And this is going straight from, not from B to C, but actually all the way from A to C. Does that make sense? Well, if that's the case, then let's see. Does it make sense that I've got, well, for my force now, I have n of a going to the right, but then don't I also have 16 going to the left? Like my force is just more complicated. Again, I'm used to having numbers for those. Like if n of a was 12, then I would have went, oh, 12 to the right, 16 to the left, that's 4 to the left. And I would have wrote 4 to the left, right? But here I don't know what NA is. Everything else stays unchanged. Actually, I'm suddenly a little bothered by something here.
Bothered by the distance.
Here's what I'm bothered by. Like this is point B, right? I'm actually doing this a little bit wrong. From B to C. It's still from B to C. It's kind of like this section isn't there. So it's from B to C, just like it was before. It's just that, is there only 16 there? No, there's actually 16. And notice, because this is, I guess what I want you to understand is, do you agree that the N of A is still there? Like it would be at that point. It's not like it's not there. I find it easier to do two equations, two unknowns, by the way, but and so, you know, what do I call this side over here? Well, you can call it N of C, or you can say, well, what's going on the other side? It's 16. It's certainly under tension, which means it's getting longer, and I want this answer to come out positive. Whether I write this as N of A positive minus 16 or 16 minus NA, it doesn't really matter. Either way, that's what's going on the left-hand side. It's not just 16. We worked our way over to that point. So I can call it NC as I did before, which is, again, in my opinion, a little bit easier.
So that's still be times 700 millimeters.
Yes, and so the rest of it is the same, 700 times AE. If this is the case, then I would, well, do kind of what I did before. I would say, you know, what's true about these? Well, just like before, in a sense, I said, let's take this one and set it equal to this one without the negative sign, or I could have just said, leave the negative sign in it. This one plus this one would equal 0.
So are you saying below is an alternative to the NA plus NB equals 16?
It's the alternative to two equations, two unknowns. And I don't really care. As I said, I tend to not do it this way.
Yeah.
Which is why I'm fumbling with it a little bit. But notice if I write it this way, just to pick one. Did you notice it's only one equation, one unknown? So by just kind of working the sections from the left every time instead of going from the left and then to the right. Because remember, we did sections a while ago and we said, you know, if you did it from the left or the right, you get the same answer. Sometimes it was just easier to do it from one side than the other. I think it's easier to end up with two equations, two unknowns. But if I solve that right there, I'm going to get the same NA answer I got before. And then, you know, armed with that, in a sense, you actually still have to kind of go back to that equation. You still have to go back to that to find the other one. Does that make sense? Which is part of the reason I don't necessarily like that method. It makes sense to me to think, hey, yeah, they're both of them are changing size, and that change of size has to be the same. logically, that makes sense to me. So I find myself doing what I did here. Notice there's no negative sign in that. Whatever their length change is, they have to be equal. Now, logically, one has to be negative, one has to be positive, because one's getting bigger, one's getting smaller. They can't both be positive, or the thing gets bigger, right? And it's not going to get bigger because it's pointing against the wall. So the fact that logically one of them has to be negative makes sense. Okay. I'm still fairly bothered by the fact that the wrong one is bigger in my conceptual understanding of this logically. I mean, it makes sense looking, if you just stare at this equation right here, if these two things are going to be equal and this one's multiplied by a big number, 700, and this is multiplied by a tiny number, then for them to be equal, N of A has to be bigger, right? That makes sense here, but it just doesn't make conceptual sense when I look at the picture. And the closer thing isn't true, because remember the section method. Does it make sense that this pipe has 16 pushing right here? But if I work my way to the left, all of that is 16. In other words, that 16 is right there. It could be thought of as right there because it's getting transferred through the pipe. It's also pulling this way, which means that 16 is also right there pulling this way. I mean, as far as C is concerned, it's not some caller that's a long ways away from it. It's the dude right next to him. Does that make sense? I like to think of this as like people holding hands, and it's like I'm getting pulled on by whoever happens to be on both sides of me. And so that 16 is getting pulled by everybody in there, right? Everybody, the people on the left are getting squished and the people on the right are getting stretched, but they're all feeling 16. Does that make sense? But the weird thing is, you know, this dude's feeling 16, but it doesn't mean this is suddenly 16, does it? Because then it would be doing all the work and then the right side would be doing none.
Makes me wonder, I don't know why it's making me think like tug of war. If
Mhm.
you could somehow have like handles on the very end, would it be more beneficial to put everybody on the very end of the rope, or would it be more beneficial to spread people out?
Right.
Because I didn't think this would be like, it's kind of weird that this isn't just 50-50, you know?
Yeah, isn't it weird that it's not 50-50? That's exactly right. And the only part of me that feels good about that is the fact that this equation right there had a distance in it. So the 700 is what caused that to have more, kind of a larger answer. Well, in the end, they weren't larger. N of C and N of A were, no, the sigmas were the same, but the forces in the end weren't the same because the sigmas, the deltas, I'm sorry, never called it the right name. So I don't know, I'm gonna have to cogitate on that a little bit more.
Makes sense though, right? Delta is a change in distance. So the change in distance was the same between the two. So between A and B,
Mhm.
you had a greater change of distance over a smaller distance. So you need a greater force for that to be applied versus a longer distance. You have that same change of distance. You're not going to need as much force in compressing it.
Yeah, I think that's going the right direction, and that's kind of similar to what Joseph thought too, is kind of that sense that there's just not as much there to do the same amount of work. They both have to move the same distance, but there's not as much distance there to do it. So therefore it's going to have to work harder. And A is going to have to work harder because it's got less distance to work with. I mean, in a sense, that's what this equation is saying, right? N of A has only got 300 to work with. And it's got to get the same job done that NC did. And it had 700 to work with. Interesting. Okay, one more. And we're done. So let me give you, especially since you don't have this in front of you, let me give you a second to study this one. So notice, okay, metric, notice it's static. This thing is floating in midair, just like, well, not like the last one. The last one was pinned between a couple of walls. But this thing is pulling in both directions, and so it's static. It would actually try to get longer then, right? It's got a certain length, whatever. But notice the drawing, like what do you notice about that end right there? Notice there's like blue around, it's like blue on the outside and gray on the inside. It could just be hollow. But yeah, look what it says about it. Same material, A36 steel pipe, has an aluminum core and it's being pulled on. But the steel pipe is on the outside and the inside is filled with aluminum. So it's got steel and aluminum. So that's why it's different color. It wasn't hollow. It's solid. It's just two different pieces of material. Notice we're asked to determine not how much longer it gets, but the amount of stress in the aluminum and the steel due to the loading. And then I get some dimensions. Now this feels like a totally different question, but does it make sense because they're glued together that however long the steel gets, the aluminum's going to have to get too? They're going to change the same because they're glued together. Now, are they going to want to change the same? No. As far as length, they will, but they're not the same flexibility. They're different materials. And so that E number, one of them is going to want to get longer than the other ones. That makes sense, but the other one's going to say, I'm not going to let you do that. So whichever one wants to grow, the other one's going to go and pull back and say, no, you can't do that. And they're going to be stuck growing at the same length. That's where our compatibility equation is going to come from this time. So just like last time, the two deltas were the same thing's going to be true here. That's not what they want to do, but they're going to be forced to do it. Last time it was because they're pinned, the same material is pinned between two walls, which wouldn't let it move. This time it does get a move, but they have to move the same. So although it doesn't look like the same problem, it really is. And the second thing is, notice they're actually asking us for stress, which means, and you know, again, this kind of thing should be hurting your brain at this point. For me, this is my second time through this because I figured it out. I figured this out like, 3 weeks ago, barely in time, if you will, to teach it to you. But now that I'm reasoning out loud about it, I'm like talking to other humans that are expecting me to make some sense to them. This is my second time thinking about it. It's starting to sink in, for me. So, when you look at normal stress, it kind of should be like, God, we've done a lot of calculations in this class and we're only like halfway done. And, wait, what was normal stress again? Remember, normal stress is equal to the normal force divided by the area. So we have forces. Last problem was kind of like, what are these forces? Does that make sense? We found the force. And here they're just saying, divide by the area and turn it into a PSI number. So that you have a PSI number instead of just a force. That's kind of cool. But notice it's just a different answer. Like they could have just said force or something like that. But notice we already knew the force. It's like 200 kilonewtons. But the problem is we actually don't know how much force is in each individual member. It's not like they each have 200. They each have some of the 200. And depending on how flexible they are, that's going to actually change how much each one is. Again, your gut reaction might be the same as last time. Oh, 100 for each. But they're not the same elasticity. So one's going to want to get longer than the other, and it's going to steal some of that 200. Now, again, I'm still not feeling super good about logically which one's going to get more. Which one's going to get more of the 200? If I looked in the back and I looked at their E values and I knew what I was talking about, I think I probably could guess which one was larger, but I can't yet. I don't have that down.
Before we had one get longer and one get shorter, so it was obvious where the negative went.
Ah,
Where's the negative go?
yeah,
Both getting longer.
that's exactly right. So we got some problems here. And then notice there's not like two sections of this. Last time we had like two different sections, and here there's really just one, isn't there? So it's like if I come over here and I draw that, and then I go over here and like chop it somewhere. And I say, okay, cool, there's 200 pulling over here. And by the way, notice the attachment part, like, is it actually attached to the inner part and not the outer part? Does that matter? St. Venant's principle, which is part of why I saved it for today, just says, well, it actually does, like that middle one's going to balloon out a little bit more, but after you get a little ways in, it'll just be like 200's pulling over there. And it's pretty much something you can ignore, especially with steel. So that's just interesting to think about. So that doesn't really matter what this attachment is right here. It's just 200. But here's where it gets interesting, because what do we have over here? Well, we have the normal force of the steel as one of the forces, and we have the normal force of the aluminum, and the aluminum's in the middle. So maybe I'll switch that to A. And then we have the normal force of the steel. And then I won't draw two different arrows because that'll make it look like, you know, there's two of them. But actually there's two forces over there. Does that make sense? They're each going to do a different amount of that work. So true to my style, I'm going to say, well, there's 200 going to the left. There's got to be 200 going to the right. Part of me would just wanted to go 200 here. Is that okay to do? Yep, it is. But notice that would mean that 200 has got to equal the normal force of the steel plus the normal force of the aluminum. Again, I could say the sum of the forces in X has to be 0, and I've got negative 200, I've got positive NS, I've got positive N of A, and that's the same equation. So pick one of those. Like if you like one of those styles better than another, awesome. The advantage of this one is it's very formulaic and you tend not to make mistakes. The advantage of this one is I can look at the picture and go, look at that, tug of war. One's going left, one's going right. They're going to be equal. Remember, because this is actually a cut though, that's what's required of this is going to tell us what's required of the steel and the aluminum. Because if it's not capable of this, then it tears in half, all right? That's the difference in this class. Statics, we just said 200, 200, sweet, nothing moves. Now we're saying not necessarily. If you choose the wrong size or material, then it snaps in half. We're looking at internally what's going on. So there's my first equation. Cool. Where's my second equation? That's kind of the easy one. It's time to switch to a different. It's my second equation. Red. So I want to give you a second to kind of think about that before I just kind of write that out, because we've got a little time. Probably still get you out of here on early. Let me get you started at least by saying, well, the compatibility equation comes from what happens to the length of the steel and what happens to the length of the aluminum. What are those deltas? How are they going to grow? Remember that, I'll write this up at the top, that equation is NL over AE. Normal force, length, area, elasticity. While you are thinking about that, I'm going to go up here and look some stuff up. I think we just looked this one up. E for this one was 200 times 10 to the 9th, wasn't it? And the T16 aluminum. 68.9. Notice that's like roughly triple. So what is that? Let's just stop and think about that a little. What does that mean that one of them is triple the other?
One wants to stretch 3 times less.
Correct. Which one? Because I don't think we've spent a lot of time like making conceptual sense of this. What does a big number mean? Does it mean more stretchy or less stretchy? Think about where it is algebraically in this equation right here. If 200 is down there, what's that going to do to this number versus 68 down there? If he gets bigger, what does delta do? if I divide by a big number, then I get a small number, right? So E being 200 means delta is actually going to get less. So big numbers mean not flexible. A big E means it's really rigid and doesn't want to move much. So the steel pipe is the one causing the problem here. Like the steel pipe doesn't want to get longer, but the aluminum pipe wants to get longer 3 times more, like Connor said. So the steel is actually going to be holding it back. Does that make sense? That's kind of cool that we figured that out.
Oh, so that makes that negative.
That's right. And so one of them actually is going to kind of have like a negative force to it, so to speak. That's interesting. All right. I stalled long enough, so let's play with this. So don't I have, well, the normal force of S, which I don't know. Now, interestingly, how long is that? How long is the steel pipe? It's the full 400 millimeters because it goes all the way from end to end. And then I've got an area. Can I just write A and E here again? No, because they're not the same. The area of the aluminum and the area of the steel are not the same, and their E values are not the same. So I don't get to be lazy like I was before. So that kind of sucks. Remember that our E value for steel was 200 times 10 to the 9th, and that's pascals, which means newtons per square meter. So that means over here for area, I really need this to be square meters, so it cancels. Let's just slow down a little bit and think about that. Well, notice that steel has an outer diameter of 80. So that means its radius is 40, which would be 0.04 meters. So notice I didn't have to use the pi over 4 because I can cut that in my half in my head. But then it's hollow. So it's missing its inner radius of 35. So would you agree that's square meters then? And then this square meter cancels with that square meter. This Newton will cancel with these Newtons, and I'll end up with millimeters for my delta, which makes sense because delta is a distance. It's a length to grow. And so it's always good to, think about that every now and again, even if you're like me, often kind of lazy about it. And so notice though, again, like that's not satisfying because it's got 2 unknowns in it. I've got how long did it get and how much force is there. So I don't really like that equation algebraically. So what about the other one? Well, it would be the normal force of the aluminum, also times 400 millimeters. That's kind of interesting. And we said now I'm going to be a little lazier, right? Because I already know the units work out from above, and so I can kind of be lazy and leave those off. But what's true about the area of that? What do I put for the area?
Radius of 0.035.
That's exactly right. All I have is a radius, like it's not hollow on the inside. So there's my equation. And so yippee-ki-yay. But again, I'm not super happy with this because it's another equation with a totally different 2 unknowns, right? So that even those 2 right there is not 2 equations, 2 unknowns. It's 2 equations, 4 unknowns, right? But what do we know about these 2 beauties right here? What do you know about? We don't know what those are, but what do we know about them? These are glued together. So therefore they're going to be the same. Now, if they were just sliding in and out of each other, would they do that? Nope. But they're glued together. Now, did they tell us that? No, they actually expected us to assume that, I guess. They probably should have told us that it was kind of glued together.
So if this was on a test and we just did the aluminum, you'd have to give us 4 points.
Yep.
Okay, that's,
Yeah, you're going to be looking now, aren't you?
like sit down with me, Doug. I got something for you.
The answer is, I don't have to do this. Bam. Incidentally, same as we, we're getting closer to the test over chapter 3-4. I have the solutions to the review that I made online, and there's a chance that I screwed it up because I don't have the luxury of looking for the right answer in the back to make, and you watch me make dumb mistakes all the time, right? But everybody gets percentage on their test if you find mistakes in it. So hopefully you will. These things have to grow. Notice I said grow. I didn't say shrink, because this thing is under tension, right? So they're going to grow together, whether they want to or not. Oh, well, that's cool, because then that means I can actually just set these two equations equal to each other, which means the two deltas go away. And then all of a sudden life gets good and I'm out in the sunshine. Do you agree with that?
But then what modules elasticity matter?
Yeah, soak on that a little bit. I'm going to get rid of all these. So am I happy now? The answer is no, because I want to be kayaking right now. But I'm happy algebraically because I just have two equations, two unknowns, don't I? Two equations with n of s and n of a in them. I might suffer algebraically trying to get an answer to this. Yeah, I love it. Notice in terms of cheating, like you could type this whole thing in, and this feels very daunting, doesn't it? Like to solve it algebraically. But let's reason about that for just a minute. So number one, what Caesar just said is awesome, which is we got a whole bunch of things in common here, like cancel out the 10 to the 9ths, cancel out the 400s, cancel out the pi's. Don't type those in like algebraically. Notice that stuff. That's just cool algebra skills, right? Second one is this whole thing right here is just a giant number, isn't it? So it's like make a number out of it. It's like 7ns equals 12na. Like bust your calculator out. I mean, if you're, don't have access to GeoGebra or Desmos or whatever, those are both cool tricks. So again, it kind of depends on the type of dude you are, but certainly don't type all that stuff in. At least go, hey, sweet, gone, and now just type 1 over 0.04 squared, 0.035 squared, 200, and then get it down from there a little bit. If you don't screw this up, you get 94.1 kilonewtons. Let's see, in my units, I did not get kilonewtons because I had this working. No, I did get kilonewtons, didn't I? Because this 200 right here was kilonewtons. Does everybody agree with that? So when I typed this in, I literally did get 94.1, and I had to be smart enough to know it was in newtons because 200 was in, I'm sorry, kilonewtons because 200 was in kilonewtons. Let's stare at those a second. Oh, of that 200, the aluminum had to work a little harder. Not a lot harder. Remember, we thought, oh, 50-50, 100-100. The aluminum had to work a little harder. Let's see if we can make sense of that. Why did the aluminum have to work? I don't know the answer to this. I'm like reasoning with you right now. Why did the aluminum have to work harder? Yeah, it's my first thought too. I agree. And it's like if it's softer, it's sort of 3 times more likely to want to change, right? That's what elasticity is, and so it had to work harder.
Yeah, but the steel's holding it back as well. So it's fighting the steel. The one that's fence, it's already thick.
Doesn't feel super good to me yet.
What do you think, Jess?
Just as confused.
All right.
I love trying to figure stuff like this out. I kind of love that sense of,
He's always like, wait, so I'm like,
No.
come on.
I don't need
Yeah.
I don't know, as you're doing these problems, like reason about this stuff a little bit. Again, I try to err on the side of not assigning too many questions out of respect for your time and so forth, but also so that you feel like you have time to maybe think some of these kind of thoughts instead of just, oh, got the right answer, I'm done. Just encouraging you to do that when you can.
Do you think it's maybe because the force is attached to the loop, but we're kind of acting like that 200 is pulling on all of it equally, so.
I mean, the interesting thing is, I haven't had a chance to talk about this yet, and I hopefully will really quick here, but the aluminum grew really big, right? 3 times bigger. And then the steel came in second and said, no, you don't. And kind of pushed it back. Does that make sense? That's another way to look at this. Actually, we're studying 4.4 right now. 4.5 is the same exact questions. It's just looking at it differently. Like here, we're saying those don't, their 2 deltas are the same. 4.5 says, let's go ahead and let aluminum make this get longer. And then we'll come back and then we'll take the steel and the steel is going to push it back. Now it's kind of back to the same size, if you will. That's kind of the idea,
So
conceptual idea.
people would do to kind of get away with using less steel, maybe.
That's a super good question. Yeah, like one of them could weather better. Like you could put a sheath around it that doesn't weather. So that's the weather ones on the outside and then the strong ones on the inside. Or it could be protection. You probably wear aluminum, so you can actually kind of scratch aluminum with a fork. So it's kind of weak. And so let's put some steel around it to protect it because it's going to get driven over by a car or something like that. So yeah, this
That would have
is,
made me think that the steel would do more work though. Like if you have 2 substances being pulled on and they're attached, you would think the stronger one would take more force. That's what I think.
Maybe.
or the other one has to work harder to do the same job. I mean, it's kind of like if I go to the gym with Ian's stronger than me. For us to get the same amount of work done, I'm gonna have to work harder because I don't have the muscles, same muscles he has.
But
And
he's still
so,
gonna pull more kilonewtons. You know, for lack of a,
right.
he's still gonna pull more weight. So you think the steel would pull more weight, but it's not.
Yeah, it's kind of, are you conservative or liberal? Conservatives would say, hey, I'm stronger, I should get more. Liberals would say, well, you're stronger, you should work more and I'll work less. Maybe we shouldn't go down that road. Are we done? Well, no, actually, because we were told to find remember this confuses me too, the normal stress. How much stress is on each one of them, right? So we actually have to do that sigma calculation. Well, didn't we just find the normal force and don't we know the area? So if we divide those, we can translate that to PSI, which again is good because that's how you make sure your material is the right size. And so what is, let's just do that really fast. What is sigma for the steel? It's 94, notice that's kilonewtons, 94.1 kilonewtons divided by the area of the steel, which we said was pi. Notice I can't get rid of the pi this time. It was this, right? So this is kilonewtons per square meter, which again is, I find myself not wanting to do that because I think of this as, well, what was our unit for that? Newtons per square meter. Did we rename that one? Like, again, I'm losing it in that regard. Like we've done so many things. Is there a name for newtons per square meter? I got it. It came to me. What is it? Pascals. So for that reason, if I look in the back of the book, I'm probably going to get this wrong, but if I rewrite 94.1 kilonewtons as 94,100 and write newtons, square meters, then I'm actually going to get this answer right. So when I do that, I get 798,745,61 pascals. Now, is that what I would see in the back? No, I'd say like megapascals or gigapascals or whatever. And similarly for the aluminum, because I had 105.9, that would become 105,900 newtons divided by pi times its radius squared, which is square meters. I get 275,17565. So interestingly, PSI wise, notice the steel is much bigger, if you will. Just for the fun of it, let's see, 3 places over, 3 places over. Isn't that going to say 27.5 megapascals? And the one on top would say 79.9 mega. Mega's million.
Oh, that adds up, doesn't it? So it's taking damn near the same amount of force, but it's such a small sheath. So it's under
Exactly.
more stress.
That's exactly right.
So it
It's
is-
tiny area, so it's a tiny, it's really strong rigid wise, but it's really, that's why converting this to PSI is such an important calculation, because it's like, oh wow, we got to choose some material there that
Or what makes
really
sense, yeah.
strong. There's not much of you, you've got to do a lot more work.
Yeah, which like I was gonna go to bed for it. I was like, there's no way because it steel's not working harder. Because it's such a small. So it'd be like you and Doug go to the gym and you're like, let's curl 40s, and Doug's using his whole like bicep and you're curling with like just 2 fingers. If the steel has a handicap, it's not as much. Makes sense. The steel is spotty, 100%.
Well said, yeah. I'm kind of wimpy aluminum. I'm going to try to lift this weight. Will you spot me? Let me just show you this really fast. I don't know. I'm trying to decide if I should show this to you or not. 4.5. Notice it says right here. I just don't want to confuse you. I mean, it's kind of cool to see. Let one force deform it and then another deform it back. This genuinely might appeal to some of you, but I'm kind of thinking maybe I'll just show it to you at the start of class next time. That way, what I taught you can kind of just sink in a little bit. Maybe I should say it next time.
You missed it, Joseph. The steel's working hard. Is it? Yep. Because it's a small sheet, so the force is like, it was almost equal. I was 94 to 105, but it's like that thin sheet is taking that much force.
Oh, yeah.
Yeah, I basically forgot about that. So we did the stress calculation, and the stress of the steel was way higher. It's drastically higher.
Yeah, I'm 100% right about that. Let's not do this today. Let's do this for 5 or 10 minutes at the start of next class. But notice this is the same problem that introduced it. This is kind of a different way of looking at it. So this might appeal to you. It's like, oh, I like that. This is called the force method. Before it was kind of like the delta method, like the deltas are going to be the same. They're going to be the same because it didn't get to move, or they had to move the same. So those 2 problems are really good. Those 2 problems will allow you to get every problem in the assignment right. You won't even notice that you don't know 4.5, basically. And then, so in this particular case, I'd recommend you try to do the 4.5 assignment like today or tomorrow, just so that when I show you this, you'll go, oh, that's interesting. And then you can either switch to it or just go, who cares? All right, I think we're good. Release yourself into the wild.